Thanks so much, Matt. So I'm just gonna dive into the topic today. So I'm going to be looking at a type of fiber optic sensing known as distributed acoustic sensing, or DAS. And we're going to be looking at some recent results from a slow-moving landslide site in the UK. So I just want to start off going over the research motivation for this work. And I think many of you here might be familiar with the Brumadinho tailings dam failure. It occurred in Brazil in 2019, and this was a very catastrophic failure where 270 people lost their lives. And so I'm just showing a quote here that was taken from the executive summary on the causes of the failure. And this is really a big part of what it led me to go back for school at the University of Calgary. And so I want to give a little bit of an overview of the technology itself. So this is just a basic slide to show you the main components of this. So we have DAS is a type of distributed fiber optic sensing. There's two main components. We have the interrogator unit, and then we have the fiber optic cable. And so the interrogator is injecting a series of laser pulses into the fiber. If there's a disturbance at any location along the cable, this will result in a change in the scattering positions that are inherent in that optical fiber. And so that scattering will then cause that incoming laser pulse to interfere in a different way, and this will result in an optical phase change. And so the output that we're getting from DAS, which in this case is the optical phase change, it has a linear relationship with strain. And so this, so we can convert our output to a strain just by using properties of the optical fiber and also acquisition settings from our interrogator. For this experiment that we'll be looking at today, we have a spatial sampling of 1 meter, and we're using a spatial resolution, which is called the gauge length of 4 meters here. And I also want to mention that we're looking at the low frequency component of DAS. So we have applied a low pass filter to our measurements, and we're looking at everything below the 1 hertz frequency. So I'm also going to highlight here that we're looking at strain, but using that strain data, we can also use this to look at changes in strain over time, or the strain rate. And we can also infer a relative displacement as well, just by integrating our strain data over the gauge length. Okay, so now that we've looked at the basics of how DAS works, let's take a look at our study site. So this is the Holland Hill Landslide Observatory. It's one of the most studied slow-moving landslides in the world, and it's located in the UK. The movement of the landslide, or the velocities, are in the range of about 0.5 meter to 3.5 meters per year. And there was a fiber optic cable that was installed at the site in 2020. This was by OptiSense and the British Geological Survey. So we can see the layout of the cable as this white line, running up and down the slope. And here as this red line, I'm just highlighting a cross section of the slope. So the cable itself is buried quite shallowly. It's at a depth of around 10 centimeters. And so now we're looking at these results from our fiber optics. So on the left-hand side, I'm showing us an animation of the strain changes from DAS occurring over this short period of rainfall. So this is showing us data from about a 2-day period. And then on the right side, I've blown up this one cable section that's highlighted in this red box. So we can see on the x-axis, we've got time. So this is about 2 days of data. And then on the y-axis, this is the distance along the cable. So up here, we're looking at this location along the scarp. Down here, we're looking at the toe. So we can see here that there's this, incredible richness of information that we can see over this short period just by looking at these changes in strain rate, which is really exciting. So why should we be interested in strain rate? How can this help us? So I'm just going to point out a couple observations that we can make out from this image. We can see accelerating strain at the scarp. We can see where the initial onset of strain changes are occurring, like at what time and at what location. And then we can also make out these interesting patterns in this flow dominant area below. So just by looking at how the amplitudes are changing over time, we can look at the speed of the strain front, which is propagating across this flow lobe area, which is really nice. So we could use this data to help us make better decisions in terms of, where should we be placing our monitoring instruments, what types of mitigative measures should we undertake. It's just really, really nice to have this type of information available. And so now I've replaced our strain rate image on the right to show us the DAS strain. And so although the strain rate is providing us much, richer information in terms of looking at accelerating and decelerating changes over time, the strain data is also very helpful just by giving us a sense of the magnitude and the location where the main strains are developing. And as we briefly saw earlier, strain can also be used to infer relative displacement. So we'll look at that in the next slide. So DAS data is proportional to an average strain over a cable segment, which is known as the gauge length, and that's representing the spatial resolution of the system. So for this study, our gauge length is around 4 meters. And so this means that by multiplying our strain value by the gauge length, we can then infer a relative displacement. And so now I've just updated this image on the right, so it's now showing in units of displacement. Along this particular section, we have a maximum displacement of 4 millimeters, so that's at this location here, and this is over a 4-meter section of cable. So this is equivalent to 1 millistrain. And the nice thing about using these units of displacement is that this is allowing us to compare our DAS measurements with nearby instruments. And so at the site, there are 2 SAAs. So if you're not familiar with SAAs, these are these inclinometers that take automated readings and they measure horizontal displacements. And so I've selected the uppermost sensor at the SAA. So this is at a depth of about 0.3 meters. And I've compared the relative displacement from this SAA with our inferred displacement from DAS. And I'll just remind us that the depth of the DAS cable is at about 0.1 meters, so they're not quite at the exact same depth, but relatively close. And I'll also remind us here that with our DAS, we are looking at an average strain over a length of cable in comparison with the SAA, which is providing us with a displacement at a single location. And another thing to mention is just the general sensitivity of SAAs as we're getting to those very small strains as well. And so on both of these locations, we can see that the magnitude of displacement from the DAS is roughly 1/2 that of the SAAs. So but we can also make out, they are quite correlated, at least when we're looking at this location, because we're missing data from this SAA up here in terms of when we begin to see that increase in the displacement, we can see that that increase happens at around the same time. So one other thing to consider that can help explain why we're seeing these smaller magnitudes with our DAS versus our SAA is that we are using a tight buffered standard telecommunications optical fiber. And so I'm showing a schematic from Fenta that gives us a little bit of the layout of the cable. So within this cable, there's different layers. The strain data that we're looking at is the strain at the optical fiber core. And so because of the effects of these different layers, there's strain transfer that's occurring between them. The cable is essentially protecting the fiber from experiencing too much strain and breaking. So it also helps to understand why the magnitudes that we're seeing in our DAS are slightly less than the SAAs. Okay, so now I just want to quickly go over, when should you consider DAS? If you're thinking about different types of projects, when might you want to consider it? And I think it boils down to two main points. So there's the scale of your project, and then there's also the severity. So talking about scale, this is going to represent the aerial extents that you have to monitor. If you have a very large area in the order of kilometers or so, then DAS could become a very attractive option. So the main expense with the DAS system is typically going to be the interrogator. So that's what is injecting that laser pulse into the fiber. This can cost roughly 150K or so. If you're interested in obtaining these quantitative strain values similar to the ones that we showed in this study. And the cable itself, if you're using just a standard telecoms fiber, this is going to cost around $3 a meter or so. So with this in mind, there is an economy of scale where the greater area that you have to monitor, the more cost-effective DAS will become. And then the other area that I want to highlight is the severity. So severity, that's going to represent, what is the consequence of failure? So many DAS systems come with available alert software. They can be configured to alert to different thresholds. They can be integrated into different security types settings. And so for areas where you're very interested in getting an alert as soon as the event happens, that also makes DAS a good option to consider. And also, as we saw in that last slide, DAS is highly sensitive to these very, very small strains. So when we're looking at these, inferred displacements much, much smaller than 1 millimeter, we can still make out these changes using DAS, which is quite nice. So before wrapping up, I do want to share this figure. So this is from a recent review paper by Casagli and their colleagues, and they were looking at landslide detection, monitoring, and prediction with remote sensing techniques. So in this figure, they're highlighting the capabilities of both ground-based interferometry as well as Doppler radar in detecting these different types of landslide events over a wide range of velocities. So as we can see from this figure, there is a gap between these two technologies. To overcome this, there can be some extrapolation using the ground-based interferometry to help with forecasting different event types. But that said, I think this is, a really nice figure to help illustrate how DAS can help to complement other types of surface remote sensing techniques. So DAS has, real-time data acquisition and transmission capabilities, and it can also capture this wide range of velocities. And it can go beyond that into being used as a seismic sensor, which I don't think we have time at all to get into this talk because I'm probably already going over. So with that, thank you, everyone. And I do want to acknowledge that this is through a MyTax Accelerate grant with two industry partners, OptiSense and BGC. And I also want to thank the Norwegian Geotechnical Institute as well for a research visit where I was working a lot on this paper, and we should have a preprint available soon. So yeah, thank you.
Thanks, Susanne. That was pretty awesome. We do have a couple of hands up, and Doug Dewar has a question. Doug, I can read it out, or you can ask it if you'd rather.
Sure. I know it's not a simple answer, Susanne, but do you have any idea of the total strain capacity of these systems, like the maximum landslide movement or the range you can handle, say in a slide and in a flow type scenario?
Mm-hmm. Yeah, no, that's a really good question. So, based on my understanding and discussions with some suppliers, I believe that at least for the cable that was used in this experiment, it was assumed that it can withstand up to about 2 to 3% strain. So just to give you a sense of the max strength for that cable, but that's going to depend on the cable type as well.
Okay, so then there's another question from James. I think we got another minute or so. How does DAS strain compare with strain gauge or an IMU strain data? It's a very pipeline specific question. And Yeah. I don't know if you know the answer to that, and if not, we can maybe follow up with James
Yeah.
later.
I would say, I would love to do an R&D project on that to find out. But yeah, I don't have an answer for that because I haven't looked at that specifically. Yeah.